This lecture has to do with formal charge. By the end of this lecture, you should be able to calculate the formal charges on all of the atoms within a Lewis structure, and also to use our formal charges in order to evaluate Lewis structures in order to decide which structures are the most important, especially if multiple resonance structures can be drawn. For more information, please read section 4.7 of your textbook. So let's start off and look at a couple structures. And the first one we'll look at is this bicarbonate molecule, HCO3-, which exists as two resonance structures. If we draw the Lewis structure for this, what we find out is we need two Lewis structures to really represent the reality of this molecule. And we can see that the double bonded oxygen can be drawn between two different oxygens on that atom, on that molecule. So one of the questions we can ask ourselves is this total anion has a negative charge. So that whole molecule has a negative charge. But where is that negative charge? Where on the molecule is it located? Is it located on just one of the atoms? Is it spread out over multiple atoms? Is it spread out over the whole molecule? We don't know. But the formal charges, they're going to allow us to be able to start to answer these questions. Similarly, we can look at another structure, carbon dioxide. We can draw multiple resonance structures for carbon dioxide. We can draw the one on the left, which is the one we've shown before, but I could also move electrons around and draw the resonance structure on the right. All I did was move electrons, so that is a resonance structure of carbon dioxide. But are they both equivalent? Is one structure better than the other? Again, what we're going to be able to do with our formal charges is be able to decide that in fact the left structure of carbon dioxide is the best one and the right one is not as important. And we'll start to understand why that is. So a couple notes about formal charge. One of the things to keep in mind is formal charges is not a real charge, but it's a measure of the electrons formally assigned to an atom in a structure, right? So this is one way we can model or think about a molecule, but it turns out to be very useful. So our formal charges are going to allow us to determine where negative and positive charges are located in a molecule, and also to be able to evaluate multiple Lewis structures and to decide which is the better resonance structures when we can draw various non-equivalent structures. So formal charge. So our definition of formal charge is it's the charge of an atom in a molecular ion would have if all bonding electrons were shared equally between the bonded atoms. One of the things about formal charge is it assumes 100% covalency. So what that means is it assumes all bonds, all electrons in a bond are equally shared, which we know is not true, but that's one of the assumptions of our model. So to calculate our formal charge, we have these set of rules, and we can also look at an equation that's shown below. This is the same thing mathematically as it does in words. So the way we find formal charge is the first thing we do is we take whatever atom we're looking at and we ask ourselves how many valence electrons are there in that free neutral atom. So we get that just from the periodic table. And then we're going to subtract from that the number of electrons we assign to it in the molecule. And the number of electrons we assign to it in the molecule are all of the lone pair of electrons on that atom and 1/2 of all of the electrons in bonds. And that 1/2 comes because we're assuming again that 100% covalency or equal sharing. One other thing to take note of your formal charge is that the sum of all formal charges in a molecule must equal the total charge of that molecule or ion, as we will see. So let's go through a couple of examples to help this make sense. So let's go back to that bicarbonate example. So I have one of those resonance structures shown, and let's go through and let's calculate the formal charges on all of our atoms in this structure. So we'll start off with this hydrogen atom. So let's calculate this formal charge on hydrogen. So we'll start off and say, how many valence electrons are there in neutral hydrogen? Go to the periodic table, we can say hydrogen has 1 valence electron. And then we want to subtract from that the number of electrons that we've assigned to it in the molecule. So So the number of electrons that we assign to the molecule in this case is just the covalent bond between the hydrogen and the oxygen. There's no lone pairs on the hydrogen, so it's just the 2 electrons in the covalent bond. So we're going to multiply that by 1/2 because that's our bonding pairs. So written out, we'd have the formal charge of hydrogen be 1 minus 1/2 times 2, or 1. So 1 minus 1 equals 0. And we see that hydrogen has 0 formal charge to it. We could do another example. We can look at this top oxygen circled in red. In this case, we do the same thing. Say how many valence electrons does neutral oxygen have? It has 6, and we want to subtract from that the number of electrons assigned to it in our molecule. So the number of electrons assigned to it in the molecule will be the 4 electrons in lone pairs, because those are only associated with the oxygen, and half of the electrons in the bonds. So there's 2 covalent bonds, both representing 2 electrons. So that's 4 electrons times 1/2, which gives us 2. So we end up having 6 minus 6 equals 0. So that oxygen, again, has 0 formal charge to it. So there it is written out in a little bit shorter hand. We can keep going through the rest of the molecule, and we can say this oxygen in between the hydrogen and carbon also has 6 electrons assigned to it in the molecule. So again, we have 6 minus 6 equals 0. We can go to the carbon, and the carbon in this case has 4 covalent bonds to it. So that would be 4 electrons assigned to it in the molecule. So 4 minus 4 equals 0. And that leaves us with our oxygen on the right, and in this case we have 3 lone pairs of electrons, or 6 electrons in lone pairs, 1 electron in the covalent bond. So in this case we have 6 minus 7 equals -1. All right, so this oxygen has a formal charge of -1. Also take note, the other thing to remember about formal charges is the sum of all of our formal charges has to equal the charge of the molecule or ion. So our bicarbonate structure has a total charge of -1. If we add up all of the negative charges, or all of our formal charges, we get a -1. If we go back for a second and consider the 2 resonance structures that make up the bicarbonate structure, all right, one of the things we looked at before was how the double bond moves between 2 oxygens, right? And we said that double bond is really not moving, but it's sort of shared between those two oxygens in our structure. What we can see now with our formal charge is the negative charge is also shared between those 2 oxygens. So a lot of times you'll hear this expressed by chemists is that negative charge is delocalized. It's not just on one oxygen, it's actually shared between both of those oxygen atoms. And you can see that with the formal charges and the negative charge I've drawn in on the structures here. So we can also use formal charge to evaluate resonance structures. All right, in order to do this, we need to go through a couple rules. The first of which is the best molecular structure is the one in which the formal charges on each atom is 0. If we can't draw a Lewis structure where all atoms have 0 formal charge, then the best structure is the one that minimizes the amount of formal charges. And if we have to have a charge, and if we have a negative charge, the best structure is going to be the one that's going to put the charge on the more electronegative element. So those are our 3 criteria for evaluating our various Lewis structures, or resonance structures. So let's start off and go back to our carbon dioxide example that we started this lecture with. We can look at 2 resonance structures. All I did was move electrons, so these are valid resonance structures. But now we can say, are these equal? Is one resonance structure better than the other? And the way we would answer that would be to first assign formal charges to each of the atoms. So if we go ahead and assign formal charges, what we see is that the structure on the left, all of our formal charges are 0. On the right, our formal charges, we have a -1 on the oxygen, a 0 on the carbon, and a +1 on that other oxygen. So here we can see the structure on the left is better because it's minimizing our formal charges. All of the formal charges are 0. We can go ahead and look at another example where we have 2 N2O molecules. All right, so in this case we have 3 resonance structures, and we want to see which, if any, of these structures are better. Alright, so again, we're going to go through the same rules. So the first thing you should do, pause this video and see if you can't assign formal charges for all of the atoms in our structures. Okay, so now we can go through and we can assign our formal charges. And when I did this, the first structure I got 0, +1, and -1. My second structure, -2, +1, and +1. And that bottom structure, -1, +1, and 0. So the question is, which of these is the best? We have formal charges in all of the molecules, so we can't use our first rule. What we can then see is the structure on the left and the bottom structure have less formal charge than the structure on the right. So those are probably the better structures. And then within those two, we want to look at and say, can we put the negative charge on the more electronegative element? The more electronegative element is oxygen. And so what we'd say is that first structure is our best resonance structure. It minimizes the amount of formal charge and puts the negative charge on the more electronegative atom. So formal charges can be really helpful for drawing Lewis structures. If you draw enough of these and calculate formal charges, you can start to see some patterns which will help you draw Lewis structures. And some of those patterns we can sort of summarize here. So second period elements, when they're in a structure, have 0 formal charge under the following cases. Right, so carbon will have 0 formal charge when it has 4 covalent bonds to it. Nitrogen has 0 formal charge when it has 3 bonds, 1 lone pair. Oxygen, 2 bonds, 2 lone pairs. And fluorine, 1 bond and 3 lone pairs. That can be helpful because a good starting point in any structure is trying to minimize the amount of formal charge. Something else to look for is when can you have resonance structures? The giveaway or the hint that you're going to have to draw resonance structures is to notice when you have some atom with a double bonded and a singly bonded oxygen to it. If you have that, there's a good chance you can draw resonance structures between them. So what's drawn in that sort of dotted red box is your hint that you're going to have to draw a second resonance structure, that singly and double bonded oxygen to some central atom. So that ends our short lecture on formal charges. Make sure you please read the book, section 4.7, and complete the short Canvas quiz after this lecture.